calculate the pH of a solution that is 0.1 molar in acetic acid, which is HC2H3O2, and 0.1 molar in sodium acetate, which is NaC2H3O2. Acetic acid is a weak acid, and sodium acetate is a salt. The sodium acetate is a sodium salt, which is a strong electrolyte, and it is going to dissociate into its cation sodium and its anion acetate. And that will be a complete dissociation, one-way arrow. The weak acid will do as weak acids do and dissociate partially. And it will slightly dissociate into hydrogen ion and acetate ion in equilibrium. So what we see here then is that we have a common ion. That common ion is the acetate ion because it is produced in both the ionization of the salt and of the weak acid. And so that will be a common ion. And so we're going to look at calculating the pH of a common ion effect problem here. The way we calculate the pH in a weak acid is using an ice table. And previously, when we had an ice table, we only had a weak acid in the solution. The molarity of the acetic acid initially is 0.1, and there is no hydrogen ion or no acetate ion if we had the weak acid alone. But now we have another item in the mix, and that is the salt, which produces this acetate ion. Since it dissociates completely and its initial molarity is 0.1 molar, we are also going to have 0.1 molar of acetate ion initially, and that acetate ion initially is from that sodium acetate. Since we have no hydrogen ion initially, this still has to dissociate to the right, and we're going to lose X of this acetic acid, producing X of the hydrogen and X of the acetate. So at equilibrium, we will have 0.10 minus X, X, and 0.10 plus X. Just as we have in the past, we can solve for this X using the Ka expression. And the Ka expression is going to be based on this dissociation. So it will be H plus times acetate ion over acetic acid. And from the problem, we know, or from our data table, we know that the Ka of the acetic acid is 1.8 times 10 to the negative 5. And at equilibrium, our H plus is going to be X. Our acetate ion is going to be 0.10 plus X. And our acetic acid will be 0.10 minus X. Now, in the past, when we had the weak acid alone, we saw that we could ignore or neglect this subtracted X in the denominator, and we could do that because this X was much smaller than that 0.10. And the reason it's so much smaller is that the Ka value is very small. So we could ignore this since the Ka is much less than 1. And that will generally be true for most weak acids. We were able to do that before. Now, can we still do it with the common ion? Well, you may remember from your previous reading that the common ion makes acids dissociate less. So this X now, in the presence of the common ion, is going to be even smaller than it would if the common ion were not there. So we can definitely ignore that X. And if the X is small compared to 0.1, it will not make a big difference whether it is added or subtracted. So we can ignore both of those X's to solve. So now from here, it's going to become pretty easy to solve for X because the 1.8 times 10 to the negative 5, and I'll convert the pen back to black here, is going to be equal to X times 0.10 divided by 0.10, which will just cancel. If we look up here at our ice table, our X is the same as our H plus, so that will also equal our H plus. So now we have our hydrogen ion concentration, 1.8 times 10 to the negative 5 molar. The pH is going to be the negative log of that hydrogen ion concentration, which is 1.8 times 10 to the negative 5. And that gives us a pH of 4.74. That's how we would calculate the pH of a common ion effect problem.